We've seen previously that the dot product can be computed based on the lengths of the vectors and, most importantly, the angle between them, the cosine of the angle between them. That can be a bit arduous, though, if we have a vector given to us in components. So how much x, how much y direction does it have? There's a surprising discovery that we can make here, we're going to illustrate here, relating how we can calculate the dot product based directly on the vector components and how it relates to the angle idea. If we take a look at a vector written in either the unit vectors in the three cardinal directions, x, y, and z, which we could write out in the angle bracket notation here as three components, and another vector, again in three components, it turns out the dot product that we defined earlier based on an angle can also be defined based on components as simply the product of the first two components. So we've got v times w, or v dot w. We take the first component of v and the first component of w, and we multiply those. Then we take the second component of each of those vectors, we multiply those. Then we take the third component of each vector, and we multiply those. If we add up those three contributing factors, or two if we're only in two dimensions, but if we add up those products of x by x component, y by y, and z by z, we get a number. And it's not at all obvious, but it's true that this calculation with components gives us the same value as we would have gotten if we'd found the angles and done the cosine and the lengths. Now, doing that as a proof to show those are the same thing takes a bit of work, but you can take a look in Hughes-Hallett and see how that works. For now, we'll simply illustrate it with one example. Let's take our two vectors here, one of which is the vector 1, 1, so up and up. We'll label our axes here. So that's the vector 1, 1, and we'll have the vector 0, 3, like so, and that is purely vertical in the positive y direction, and we know we're going to need the angle, and because this is a nice 45 degree here, it's also 45 on this side, or pi over 4 radians. So let's calculate the dot product in two different ways. We're going to use the angle definition first. So let's say 1, 1 dotted with 0, 3 is going to equal the length of the 1, 1 vector times the length of the 0, 3 vector times the cos of the angle between those two vectors, which was pi over 4. Now the length of the 1, 1 vector is 1 squared plus 1 squared. That's then square rooted, so we're going to get root 2 for that. The length of a vector that's purely vertical, but length 3 is just 3. And cos of pi over 4 is 1 over root 2. Now there's a bunch of root 2's running around, but fortunately they cancel, and we end up with a dot product of these two vectors being just 3. Now what about this new definition with the components? So if we take a look at our component definition, we're going to have 1, 1, let's clean that up, 1, 1 dotted with 0, 3, and again that system is to take the first component of each and multiply them, and then the second component of each and multiply them and add those resulting products. So we'll have 1 times 0 plus 1 times 3, that's 0 plus 3, and that's also 3. So this is not a proof by any means, but it's an illustration that two not closely related vectors, when we take the dot product using both definitions, we get the same value, which supports our argument that we can use those two interchangeably. Now this lets us do some more creative things with vectors. In terms here of a design question, we'd like to find a vector u which has two components, x and y. We want it to have a certain length, and we want it to be perpendicular to this other vector. So we've got a vector 3, 7. So let's illustrate that. So a little bit over to the right, more up, something like that. And we'll try to draw that a little straighter here. There we go. So let's say that's our vector 3, 7. Usual x and y axes. We're looking for something that's perpendicular to that, like so. Well, how can we track that down? It's not obvious immediately how we would go about building such a vector, but once we have our dot product idea, then we can get there. So we're looking for vector u, sorry, we already have a v. We're looking for a vector u that's perpendicular to 3, 7. And if you've used the dot product before, this should come immediately to mind. Oh, I'm looking for a vector that's perpendicular to 3, 7. Well, that means that u dotted with 3, 7 must equal 0. Otherwise, they wouldn't be perpendicular. If they're perpendicular, the dot product is 0. So here, the dot product being 0 is something we're taking from the angle definition, but in terms of identifying what vector we want, what u is actually made up of, there we can use the component definition. So this is from the angle definition. Two vectors are perpendicular if their dot product is 0, and then we say what is the actual value of that dot product using the components. Well, it'll be 3a's plus 7b's. And we want that now to equal 0. And again, there's an easy solution. We could have a equals 0 and b equals 0, but that means that our u would just be 0, 0, which has no direction, and 0 length. And that's not what we're asked for in the question. We're asked for a vector with a length of 1, so this can't be what we're looking for here. So we have to get a little more sophisticated, but what we can say is how a and b are going to be related. So we can solve for a, let's say, which would be negative 7b over 3. And that would give us some idea of how the x and y components of this vector are related. Now, there's a couple different ways we can go here. Some people have learned different approaches. We can pick any value for b and then get a value for a, but we want the magnitude to be 1. And if we want the magnitude to be 1, then we're going to have to be a little careful about our choice of a and b. In fact, in particular, our a squared plus b squared must equal 1, so a is also equal to the square root of 1 minus b squared. Just solving for a here. Well then we have a in two places, and we can combine these two equalities and say we want the square root of 1 minus b squared to be the same as minus 7b over 3. And we'll take that down and start down here again. Actually, let's do this on the next page, just to polish this off. That's what we're going to use at the beginning of the next page. Square root of 1 minus b squared is equal to negative 7b over 3. We want to solve for b, so let's square both sides. So we get on the left 1 minus b squared, and just being careful to square everything that we see here. 7 squared, 49, b squared, 3 squared is 9. Bring the 9 up, we get 9 minus 9b squared is 49b squared, and we can bring that over. 9 is going to be 58b squared, so b is going to equal 9 over 58, and the square root of that. And so we can also take a plus or minus there. Let's just see what happens when we get b being the positive root. So b is 9 over 58 square rooted, and our a, which goes with that, was the vector minus 7b over 3, and so that would be minus 7 over 3 square root of 9 over 58. we can really simplify this. This 3 and this 9 are going to be able to cancel out in a second. Depends how you want to look at that, but we can think of this as the square root of 9. 3 is the square root of 9, and so these two will cancel. And so we'll get minus 7 times the 1 over root 58. If you like, you could write that as minus 49 over 58. Bringing the 7 inside the square root, we square it. Either one of these is fine. Now what do these look like though? Again, going back to our picture about the vectors, we have the 3, 7 vector. That's the one we started with. And what we just have now is our u, which is, well, it turns out both of them have a 1 over 58 square rooted with it. The a is a minus 7 times that, and the b, if I brought that out front, would be a 3 times that. So it's a common factor times, most importantly here, negative 7, 3, or lots to the left and a little bit up. And if we draw that like so, let's draw, no, that looks about right. We will get perpendicular vectors here. That would be our u. So that's not a bad way to go about it. We use the two constraints that we were given, one that the length of the vector had to be 1, and the other one that it had to be perpendicular, and so its dot product with the 3, 7 vector must be 0. And we obtain an answer for u here. Of course, there's other possibilities that we didn't mention because we also had our other b value, which was negative 9 over 58, all square rooted, and that would have led to a positive 7 square root of 1 over 58, and that would have been another vector of 1 over root 58 times, in this case, the a was first, a was the x, so 7, and then negative 3 for our other vector, and that would have looked like, here's our 3, 7 again. This would have been mostly to the right and then a little bit down. Mostly to the right and a little bit down, like so. And that would have been the alternative possibility. And we notice that those are two options for u, and they're just pointing in the opposite direction of one another. They're both length 1, but we can choose either one of them, and they'll still be perpendicular to the original vector we were given, 3, 7.